So Coq works in somewhat the same way, except you don't actually really, the style of programming is different in that you don't really write the expressions directly. What you do is you use these tactics, which basically sort of write the expression for you, because some of these expressions can like get a little unintuitive if you're not already like really familiar with the Curry-Howard correspondence. So I basically had a simple proof, and so the nice thing about Coq, like Agda, is that it's interactive, which means that you basically see how like you're progressed in the proof as you're going forward. Let's probably introduce like what Coq does. So basically, in software, we write like code that has bugs and stuff, and we use things like type systems and unit tests and whatever to sort of check that. Because computers can automate that sort of stuff. But if you're writing a mathematical proof like by hand or using LaTeX or whatever, how do you make sure you don't accidentally do like an incorrect step that basically makes your proof invalid? So a tool you can use is you can actually utilize a computer. In fact, it's actually utilizing a type checker to basically check your mathematical proof and make sure that you didn't do like an illogical step. Coq will just reject your proof if you did something wrong. So, just gonna, that is really small.
Can we say something about setup real quick?
Yeah.
So I threw him on Coq.id just because it was kind of quick to get going. If you want to be able to follow along and type check things as he goes, if you haven't done this before, I would actually suggest just doing Coq.id for now. Normally when I'm doing Coq at home, I use like proof general and Emacs, and it knows how to invoke the compiler, but I would just do that for now.
Yeah, I'm more of a like IDE type person anyway, so I use Coq IDE.
Ah, there you go.
Yeah, I don't know Emacs.
The proof general thing for Emacs is like an IDE anyway.
I think it's just Control plus to zoom in.
Oh, you're trying to zoom the text?
Yeah, and
There's another way to solve your problem. We can just change the resolution.
Yeah, so just more zoom in. Try it. How's that?
good.
All right.
Yes. Control. Did you do like Command plus?
And Control Shift plus. It says Command plus, but
Okay, so first I'm going to do a bit of boilerplate. And so you have these controls up here that basically evaluate the proof up till that point in the file. So the evaluation with the interactive editor is very linear, like in the same way your code is. It matches it like 1-to-1. So
I think it's 8.5.
yeah, that's what. 8.5p1, or is it the latest one?
I think it's P1, P2.
Maybe I should save it. I don't know. Ah, what happened?
Probably closed it. just hit clover key space, and then type in COQ, and then just hit enter. Okay, sorry, it's 8.4 PL5. Sorry. Do you need a newer version?
I don't think so. I just need to. Okay. So basically, in order to, so when you write proofs on paper and you are interacting over like natural numbers, like we're functional programmers, so we tend to like recursion over iteration, right? So basically, in mathematical proofs, you'll often do something called proof by induction, which is basically you prove, it's casework. So there are two cases. One is you have to prove it for n equals 0 or n equals whatever your lowest value you want to prove it for is going to be. And then your next step is to assume that it works for the number that comes before n, and then you use that to prove that it works for n. And so what you get is, and so if you prove both of these things, you get this sort of chain that lets you show, oh, it works for any number, because if it works, so for example, if we wanted to prove some sort of property about 5, if you prove that n implies n plus 1, like the property, then you show it for 4 implies that it works for 5. But then to show for 4, you can use 3, and then it just keeps jumping back and forth until you get to 0. And then you prove it for, and then that's your base case. So yeah, it's basically like recursion, except with proofs. And so this makes it really amenable to using algebraic data types, and we can actually define, and so what we actually do is we define natural numbers with something called like piano representation, which basically you make your numbers an algebraic data type. So it looks like this. So inductive is the keyword that introduces the type. The type we're gonna, this is the name of the type. And so this is a little strange. Basically, there's a thing called, I think, universe levels. And Coq has two main universes. So basically every type is of the, okay, right. So Coq is a dependently typed language, which means that so that means that types are values, and so every value has a type. So your types also have a type. So they're called like kinds, I guess. And so the kind of nat is set, which basically means it's a normal value. And so there's another kind called prop, which basically corresponds to propositions, which are things that sort of have like a true false to them. And we'll get to more of those. And then there's like a super kind called type, and some things aren't in set or prop, so they need to be in type. But your standard algebraic data types can just be in set. And so it uses GADT notation if you've ever used Haskell. Basically, what this is saying is that O is a nullary constructor of the nat type, and S is a unary constructor that takes a nat to create its nat. And so the reason for this is that the dependent typing, we typically want to allow the generalized algebraic data type use case, which is constraining the type of the output based not only on like just simple polymorphism. And so we've defined this type called nat. And so you see here, it also defined these other things. Basically, it allows you to do, it basically automatically creates this underlying proof term that you can use for induction hypotheses. So under the hood, it'll use this to, when you do an inductive proof, it'll use this to create the proof term. And so I'm going to get rid of this because it's actually defined in Coq. And so common syntax is like SML or OCaml. So the example we're going to use is so triangular sums are basically you do 0 plus 1 plus 2 plus 3 plus up to some number n. And so that's equal to n times n plus 1 over 2. So that's like the closed form expression. And so first we need to define a function that adds this list of numbers together. So we want to define a function that sums to the natural number we give it, and it'll return a natural number. So what we'll do is we'll basically do, so we have our 0 plus 1 plus 2 plus 3 plus. So first we're going to try doing like so defining it this way. So you add the 0 and then recursively add the rest of the numbers. So that means you'll need a helper function. That we basically have both lower and upper bounds. And some type annotations are optional, but because Coq is dependently typed, it does not have like full like HM type inference that you find in Haskell. So sometimes you'll need to write out the types. I think here it should be able to figure it out. So basically we say, so we have our lower bound and our upper bound. So if our upper bound is actually less than our lower bound, then we just return 0. So how you do less than, like to return a Boolean in Coq, is with this LTB function. And there's a reason why we don't use the less than symbol, which we'll see later. So if m is maybe it should be this way. If n is less than m, and we're going from m to n, then we return 0. Otherwise, we return m plus sum from 2. So instead of writing m plus 1 here, we'll use the data constructor we have. Instead of calling the plus function, we'll just create it directly. it's a lot simpler. So let's try this. I think they changed some of the functions. Sorry, I'm trying to find what this function is called in 8.4.
What function is it?
The less than that returns Boolean, so not the.
We can crowd search for you. Is it LEB? Less than equal to?
Maybe that is in there.
It's from the bool library. Send it to be important.
Sorry. So when I took the college course on Coq, we followed a textbook called Software Foundations, and they defined everything like within their own like textbook. So I don't know if what everything's called in like the standard library. And like the standard library for Coq is sort of separated in a strange way.
LTB underscore LT. So some of these are from the Cockable library. Do you need to, I don't know if you need to import libraries in this or not.
You do, I think I just found it. So if it's less than or equal to, so yeah, I guess we'll encode less than with, okay, if n is less than m, then the successor of n is less than or equal to okay, so that's the error I wanted to get. So it's saying, okay, sum from 2 isn't here. So you need to, so unlike Haskell, but like OCaml, you need to basically say whether a function is recursive. So this is like your let rec. So this basically says, oh, this function is recursive. Okay, so now this is a strange looking error. Cannot guess decreasing argument of, well, fix. Fix is, I think Coq uses a fixed point combinator to, it changes your recursive functions to fixed point under the hood. So you're like, what is this decreasing argument stuff? So in Coq, because it's used for theorem proving, in order to have a consistent logic, you can't have infinite loops. So Coq is, in fact, not a Turing-complete language because it doesn't have infinite loops. So it's actually really picky because you need to be able to prove to Coq that your code doesn't have an infinite loop in it. And so how it does this is every recursive call you make has to basically make at least one of the arguments smaller, which means that it needs to basically unwrap a data constructor and take another, like a smaller version inside it and use that as the argument. So right now we're actually making it bigger because we have sum from 2 mn, and we are making the left argument bigger. And so it's like, I think this might go into an infinite loop. You can't write that. And so we need to change our approach to instead basically do it the other way. And so let's we need to basically do like this, or if this is easier. So this is the approach we're going to actually take. All right, I did write this. So this would have been sum from 2. So this numeral 0 is syntactic sugar for the O constructor here.
So that data type is, the null array constructor is 0, and then if you give me a number, I'll wrap that into this type. Is that what I mean?
Yeah, I'll wrap it into this data constructor.
Okay.
So basically, if I want to have the number, so actually, I wonder if this works. No. Okay.
So is inductive a little bit like a type class where you have to define the 0 and the successor?
No, it is. It's basically the same thing as like your standard data type in Haskell,
Okay.
except that it's a GADT. So if you've ever looked at the extension for generalized algebraic data types, it's more like that. It's not really like a type class because it's just a type.
Okay.
So, I'm sorry, go ahead.
I just wanted to understand how Cock knows that O and S mean what they mean inductively.
That they mean 0 and 1
Yeah,
plus?
yeah, that it can swap out 0 for that.
Oh, that's internal stuff. This is a predefined data type.
Okay.
And so it knows that, okay, so human beings actually write numbers with digits and not with like these linked structures. So we're gonna make their life slightly easier.
Got it.
So the inductive part in that data type is just an arbitrary thing to let humans know what you're talking about. It doesn't mean anything to cock.
This keyword?
Yes.
Yeah, so it's a keyword to basically says this following thing is a data type definition. As opposed to like this says, oh, this is a recursive function. And this says, oh, this is a not recursive function.
So inductive is meaningful there.
Yes.
Okay.
Yeah, it actually got the running time. So you have like a code at that time now?
So the operator is math, not inductive.
Okay, yeah. So the number 3 is S of S of S of. It's that under the hood. And so the reason for this is because it basically turns your mathematical induction from like high school or whatever into structural induction, which is a lot more common in general. And you've probably seen this. If you do induction on like your list, you're doing structural induction because you're inducting over the structure of your data. So this is a bad definition. Yes, great.
There should be a plug on your desk somewhere.
So these two have things in them.
Here. There's a reason why I got to focus around.
Yes, thank you. Okay. Yeah. I put the code on Slack, but it's more fun if it's a surprise. And so, yeah, we need to write it a different way. The only reason I did this was to show that Cock needs to, basically you can't just write arbitrary recursive functions. And so it's still going to be recursive. And so this is basically our case of in Cock. It's just a different syntax. Otherwise, it's basically the same. So if you're summing to 0, then that's 0.
Is that 0 or no?
So they're equivalent. They're 0 and this big O are equivalent. Yeah. So I guess it's kind of nice if the font is, you're confused, then it doesn't matter here. And so if it's the successor case, this S case, then we basically read P as n minus 1. So that's how we think of it in our heads. And so we want to say, okay, so if we go back up here, we see, okay, it's n, and then this is the sum from sum to n minus 1. which is this P we unwrapped. Yeah, okay, apparently it likes to interpret your comments. So yeah, so now it says, okay, it's decreasing on the first and only argument because the recursive call, all recursive calls use a smaller argument than the original one, than this. So P is smaller than SP because P is contained fully within SP, and SP is our argument.
How'd you get that to show up? Sorry, I didn't catch that.
Just when you, like, I should. Basically, just when you click the arrow down and define the function, it'll give you this, like, message. Oh, this is defined. So I go back up and I click.
Oh, I got it now. Okay, I did the all the way to the bottom.
Yeah, so it, like, erases the messages. So now, since we have our function that basically defines this triangular sum, we can state the theorem we want to prove. So I'll write the full signature first and then I'll explain it. Okay, so this for all is basically, it's kind of like your it's like your generics or parametric polymorphism in Haskell or whatever, but because it's dependently typed, there's no real distinction between values and types. So in a language like Haskell, you say for all type A, you have like list of A. So A there is a type. Here we're saying for all n that are numbers. So from a programming standpoint, this is a little confusing, but from a mathematical standpoint, it's just like how you would write it. Like you're saying, oh, for all n, this property holds. And so this basically brings this into scope that you can use here.
Now, is that saying that n is of type nat, or that n has fulfilled the nat type class, or something else like that?
No, n is of type nat.
Okay.
Coq has type classes, but I don't know anything about them. So yeah,
So that's bringing it down to a concrete type. As if I were to say that it's list of char in Haskell, or integer, or float, or whatever.
so nat is the type, and n is just a number.
Right. N is the variable here, correct?
Yeah.
Yeah, okay.
Should I explain GADTs more? Like, so basically what this means versus... I might do that later, in case unless anyone wants me to do that now.
You haven't actually indexed the type yet, so we can wait, right?
Yeah.
Okay.
So this equals here doesn't mean what it means in basically any other language that you've heard of. So that's right. So you can use this check. And so Coq isn't as nice as Agda in defining its syntactic sugar. You use this weird notation command that I tend to try to avoid. But so I think this ek is the same thing. And so we see this is the type of ek. So it basically takes two things and returns this prop that I mentioned earlier. Prop corresponds to basically a proposition, and a proposition can be something that can be proved true or something that you can't prove true. But you can't prove a proposition false. What you do is you basically have an empty like void type called false, and you if you remember the ex falso quod libe thing from the keynote, the opening keynote yesterday, that's actually I recognize that as the name of the function we used in our course. The equivalent name in Haskell is absurd. Yeah, sorry if that doesn't make sense. It doesn't really need to. So the point here is, ECK is not a this is not the equality function. It is actually a type constructor, yeah. And so it basically takes whatever this left-hand side is and whatever this right-hand side is, and wraps that in a type. So the arity was like something to prompt. And so in Haskell, this might be star to star to star, except that these can be values and not just types. So here, these are values. This is going to evaluate to a NAT. This is also going to evaluate to a NAT. So here we have so that's the type signature of this equals. And so this multiplication is standard multiplication. And so what we've done is we have defined a logical proposition as the type of this theorem. And so this basically relates back to the Curry-Howard correspondence of this is going to be the proof that witnesses this proposition. So this is a term of this type.
Is the proposition something we're asserting or something we're asking it to prove, to check for us?
So,
Like if we could write this wrong and it would say no. Right?
so if you wrote the proposition wrong, it would still be a type, but you wouldn't be able to produce a term of that type. So you couldn't use it in proofs. So,
But we can ask, are we correct in this? Or is asking correctness just generating something in that type?
so you can't actually prove something incorrect. So I can't directly say that, I couldn't find a proof that this is correct. It must be incorrect. It could mean that you just don't know how to find the proof for it. So basically, in order to prove something false, you have to generate a contradiction. That's the way to do it. Does that answer your question?
I think so. I guess I'm wondering, like, if you change 2 to 3, what happens?
If I change 2 to 3,
What's the feedback?
the feedback is I wouldn't be able to write a proof like this.
Okay.
So basically it's not, so this is the part where you have to sort of like use your own brain rather than like relying on this, is that, I can't prove, so writing these cock proofs can be really hard. So you don't really know, am I not in the right direction to find the proof that this theorem is correct, or is this theorem not even correct?
So if I ask Coq to prove like x equals x plus 1,
Yeah.
it might not immediately tell me you're being silly somehow.
Yeah, like something that simple it might. But like in general, no, it can't just decide, this is wrong.
I think my simple way of asking my question is the top part of the screen is green because it checked that and said that's fine, right?
Yeah.
But it doesn't do that for the theorem is what I was wondering.
So,
But the theorem is not really checking your proof, it's just generating
right,
something.
it is. So basically, I think this is like a forward declaration sort of thing. And that once you have completed your proof, this triangular closed form will be available as an expression you can use to prove other theorems.
Were you in the active talk? You remember how whenever you did the left-hand side of the pattern match, you would keep adding goals to the right-hand side? This is, remember that? That's the little like control U thing? They had little brackets and numbers. Those are goals. Like when you use a proof, it's dependent on programming language that people use in the proof system. They talk about goals. You see how to create a subgoal? That's like a theorem to be satisfied. It's waiting to be proven. Just like when you write the left-hand side, of a definition of a function, fine, you've written the left-hand side, but the right-hand side actually remains to be seen. It remains to be seen that you can satisfy the type on the right-hand side. This is kind of like that. It's just that they do it kind of more non-linearly. Because when you're working in a persistent, you kind of want to just kind of throw some stuff out there and then start kind of working out piecemeal.
So they're going to start using this elsewhere, and that's when we'll learn.
Yeah.
Sort of.
Well, you have to actually write proof to use it, but yeah.
Right. Okay.
So the idea is that the structure of your proof is going to sort of look like how you might do it like on a mathematical paper proof. Of course, because it's a computer, it doesn't always work out that way. If only you could write human sentences as computer programs for like software. Okay, so we have this screen here, which is going to be where we're actually going to spend a lot of time looking. So it says you have one subgoal, and it says this is a subgoal. So it basically says, in your proof, this is what you have left to prove. And so basically, you use these tactics that basically say you can prove whatever you need to prove if you later give me a proof of something simpler. And so we'll see that. Okay, so what happened here? So above this line is what we call hypotheses. These are basically things that we have shown true. So in here, it's an assumption. So we're going to assume that is true for the other part, for this part. So the hypothesis is something that we can use as true to prove here. So here it's a little different because there's not really because this is not a prop, this is a normal type. So it says, okay, assume that there is a natural number, and so that's not really corresponding to a property. But a lot of the hypotheses will have right-hand sides that look maybe something like an equality or something, and basically you're like you are able to say, okay, we already know that whatever this hypothesis is true. I don't think I have anything. Oh wait, I do. And so our overall approach is induction. So there's a tactic for that. And you say the variable you want to induct on, and is this squeaking? Just notice that. And so we have this notation here. So I'll just write it. Basically it says, okay, so for your cases, this induction is going to basically give you more information for each case that are specific to each case. And so the zero case, there's no really extra information there. In this case, in the inductive case, we have, okay, so this is how we're going to bind the inductive part. So the inductive constructor here is this S, which contains the previous number. So we need to bind that to something. So we bind that here. And then, in proof by induction, for the inductive case, you assume that the previous version of the thing you're trying to prove holds. And so we're binding that to this variable here. These are actually optional, but it'll automatically generate names for you if you don't do this. So So if we do this, yeah, you can use admit to basically say, skip this, which is good for when you're actually interactively doing the proof. So I want to do this subcase before this one, but it's not going to let you like actually do stuff with it. So it basically automatically generated n as the previous number now, and this IHN as the inductive hypothesis. And so that can be a little confusing. Of course, once you've been like laboring over like homework assignments, you start to like care less. So my later assignments have me just, okay, just give me whatever names, and then they give you like H1, H3, H14 and crap. Okay. So now it says 2 sub-goals. This means that you now have 2 separate things you need to prove if you want to end up completing this proof. And so you prove them one at a time. And so a nice thing that you can use, I don't know if you can use it here. Can you? Okay, so there are these things called bullets, which are basically let you, okay, so this is kind of hard to see, what am I actually doing right now? I need to like focus on one of these 2 things, but they're both on my screen because I need to prove both of them. This hyphen will focus in on one of them so that this looks easier. And it also ends up making the code you write here look better, because if you're doing a proof by induction on paper, you're doing casework, you're probably going to want to like bullet each case so they don't all flow together. Okay, so now we have to prove that sum to 0 times 2 equals 0 times 1. So let's see if Coq is smart enough to say, yeah, this is true. So basically what I did was I asked Coq to use its automatic tactic. So basically it basically does a search behind the scenes, and it can be really powerful but also like really like unpredictable. It uses these like search techniques. So in simple cases like this, you're actually, because each of these things is like doesn't have any variables in it, Coq could just evaluate these 2 functions and you'll be able to see that they're equal. So if we didn't want to do this, what we could do is basically, so sum2 is a function. So unlike in software engineering where you use functions to abstract out like procedures, so if you give if you're a library and you expose a function, you don't expose how it's implemented. Here, you kind of do. So it will actually, it actually uses this definition. This definition is available to you when you're proving things about sum2. And so one thing you can do is unfold. And, well, since that was 0, it automatically generated the case. But I guess I'll show unfold later. Okay, and so it needs to prove that 0 times 2 is 0 times 1. And so let's just say, okay, simplify everything as much as you can. And so we need to prove 0 equals 0. That's kind of trivial. So basically at the bottom level of these proofs is so this is known as reflexivity. And so we just say reflexivity. And you can use this tactic when both sides look exactly identical. well, okay, so implicitly reflexivity will do a simplify beforehand, but at the strict level, it's to prove two things that look identical. So two terms that look identical. Yeah.
What's the difference between reflexivity and trivial?
I think trivial is more, like, proves more stuff.
Oh.
I was referring to trivial as like the word trivial.
Yeah, sure, sorry, I was just
Yeah.
trying to,
Yeah, you could use auto here or whatever, but, so yeah. And so, actually, if we have time later, I can show what, actually, I'll just show it real quick. I'll show it later. But I'm just going to replace this with auto because Cock is smart enough to know how to do this. So now we need to prove our inductive case. So it gives us the inductive hypothesis in our list of hypotheses. So this is the proposition, like the fact that we are assuming is true, the previous case. And this is the name we're giving it. So this is the proposition, and this is the name of the particular proof that we're assuming exists. Typically, you don't really introspect the proofs once you have them. So you sort of build them up, but from there, you sort of want to use them as black boxes as, okay, inductive hypothesis is a term that proves this. I don't really care how it's constructed. In fact, there's a thing you can turn on that basically says if this right side is a prop, and you have two terms of that prop that have the same type, then they're considered equal, but that's not turned on by default. Okay, so here we have sum2 here, and so let's start with that. And so what it did is, so we had a sum2, okay, so let's go back. We had a sum2 of a successor. So basically we know a little bit more about the argument here. We know exactly which case this is. So it goes into the definition you created and replaces it with the right-hand side. So it replaces sum2 of SP with n plus sum2 of P. So actually, when you define a function, how you write the function can make a difference in how stuff is proved.